two announcements. Tomorrow and Friday we will not have it. No class tomorrow. क्लास देके भी फायदा नहीं है। Friday तो पढ़ा है किसको? I have counted total number is at least 63 or 64 out of 180. What will happen remaining 120? And whatever the topic we are doing, it is slightly more intense. We require your attention here. Otherwise, you will be lost. Okay. So no class tomorrow and no class on Friday. Also, the tutorial will not be there on Friday. Okay. So we will have a class on next week Tuesday, and whatever the classes we have missed, we will try to make up next week. There will be online class for 2 hours. Okay, 7 to 9 we will have an online class. Take the 6 to 8, okay to everyone. Online class, maybe on Tuesday or Wednesday. It's okay. Tuesday or Wednesday, we can have 6 to 8 2 hours class. Wednesday 6 to 8 evening we will have a extra class. So whatever classes we have missed this week, that we will make up. Okay? Okay. So let us start with root locus. Remember in the last class when we started looking at the stability of the feedback control system, we said भैया मैं बोल दूं नहीं कुछ करना हो तो कर लो पहले फिर बाद में बात करेंगे ऐसा कुछ है कोई इम्पोर्टेंट बात है जो बाद में नहीं बताई जा सकती है ना आप फिर कॉन्सेंट्रेट करो मेरे सामने भैया कुछ स्पेशल बताना पड़ेगा आपको भी कुछ ऐसी विशेष बात हो जो अभी करनी होगी तो कर लो अगर नहीं है तो फिर ध्यान दो आगे ठीक है ओके so feedback control system okay if you wanted to find out the stability of the feedback control system what you have to do you have to find out the roots of the characteristic equation and if all the roots of the characteristic equation are located on the left hand side of the imaginary axis then my system response is stable isn't it that is what the stability we have discussed isn't it then we argued saying that typically the processes which we deal with usually have the order of the S will be more than 3 or 4 where finding the roots will not be easy isn't it finding the roots will not be easy and therefore this Raoult stability criteria came into the picture क्या है कुछ विशेष बात हो तो बताओ बाकी लोग भी जानेंगे मतलब आपकी मंद मंद मुस्कान तो यही बता रही है कुछ विशेष बात है ऐसा कुछ है कुछ ऐसी विशेष बात हो तो बताओ सब लोग भी हंसेंगे तेरी ऑल्सो हैव स्माइल इज कंटेजियस चलिए आप कुछ बताओगे तो बाकी लोग भी हंसेंगे ओके so then we said finding the roots is not easy and that is the reason this Raoult stability criteria came into the picture because you can find out the stability of the control system even without finding the roots. That is that. You can find out the stability of the control system even without finding the actual roots. But then we argued again. We said, okay, stability we will be able to find out whether the control system is stable or not. But we will not be able to find out the dynamics of the response. We will not be able to find out whether the response is going to be oscillatory, non-oscillatory, how far you are from the stability, on the verge of instability, isn't it? Correct? So how much is the margin of the stability? All those things you are not able to get by using Raoult stability criteria. And that is very, very important. Why? Because in a real life practice, you don't know what is the actual value of the time constant. You don't know what is the actual value of the process gain, isn't it? Depending on how accurately you have performed your experiment, your tau and km or k values are going to vary. And if there is a error in this, whatever the stability you are finding out by using Raoult stability criteria may not actually be there in your actual system. So in such cases, you definitely want to read how far you are from the verge of instability, isn't it? What is the extent of stability you are having? Okay, correct. So in order to find out these things, you need to find out the location of the roots exactly, where the roots of the characteristic equation are located. Okay. So then again we came back again to the same point. We said okay, stability we can find out, but that is not the everything. We require the location of the roots primarily because we wanted to find out the dynamics of the response. Okay. Then we started looking at the root locus. Now what is root locus? So remember, in this entire characteristic equation, the only constants which are corresponding to the controller are the parameters which can vary, like Kc, tau I and tau d. These are the only parameters which can vary. Okay. Now we are trying to find out, let's say value of Kc is changing from 0 to infinity, how the location of these roots of the characteristic equation are going to vary in a complex plane. And that locus of the roots of this characteristic equation in a complex plane, that we refer as a root locus. Okay. If you look at the root locus starts at an open loop poles and it terminates at open loop zeros. What is open loop poles? Open loop poles are the poles when you are putting Kc equals to 0. Remember, in this particular equation, see, if you put Kc equals to 0, this term goes away. So you are actually finding out the open loop poles of the process directly. Remember, when Kc is 0, you are getting the roots as 1 by tau 1, minus 1 by tau 1 and minus 1 by tau 2. And as the value of Kc increases, what will happen to these roots? These roots will move towards each other. They will meet at a constant point here where both the roots are same. And then at this point, the real part is going to remain the same and their imaginary part will become, their imaginary part is going to increase and that will become infinite if you are increasing the value of Kc to infinite. And such arms which are actually going to a infinite, these are referred as asymptotes. These are referred as asymptotes. Okay. We will define all these terms again. Right? ध्यान दे दो, ये समझ में नहीं आएगा. We have started a very complex thing. I am telling you, you will not be able to get it. आपकी किताब में भी नहीं है ये. इसके आगे वाला पार्ट आपकी किताब में भी नहीं है. So please pay attention. Okay. So this is a very simple case where there is a second order system and only the proportional controller is there. We are finding out how the roots of the characteristic equation are going to vary with respect to variation in Kc from 0 to infinite. That is what we have plotted, isn't it? So locus of the roots as Kc value varies from 0 to infinite is referred as a root locus. Is it clear? Is the only root locus? Is the only root locus defined in the book, but it's not the only root locus possible. Okay. There is another type of root locus is possible. Remember, what is Kc? Kc is the parameter of the controller. But there are other parameters also in control. Isn't it? You can have tau. So let's say if you vary the value of tau from 0 to infinity, how your roots are varying, that will also be referred as a root locus. If there is a parameter tau d, how the tau d is varying from 0 to infinity, that will also be referred as a root locus. But in most of the books, you will see only Kc is varying from 0 to infinity. It is not there in most of the books. Okay. But even those cases are also referred as root locus. Okay, is it clear? Okay, now let's look at slightly more complex case. So in this particular case, the process transfer function is given as 2.98 s plus 2.25 divided by s plus 1.45 into s plus 2.85 square plus s plus 4.35, and again for a simplicity we have assumed that gm, gp, gm and this should be gf. Sorry, it's not gp, it's gf. Gm and gf is equal to 1 and gc equal to k. Okay. So what will be the characteristic equation? 1 plus gp, gm, gf and into gc should be equal to 0. This is the characteristic. So when kc value is 0, in that case what will be the roots? When kc value is 0, in that case the roots will be directly obtained from this process itself. Isn't it? So roots will be, s will be minus 1.45, s will be, again there will be multiple roots which are located at minus 2.85. Isn't it? And then there will be another root which is s equal to minus 4.35. Correct? So that is what you are getting. So see, these are the roots which you are getting, and these roots are open loop poles. These are called as open loop poles. So when controller is not connected, then these roots are called as open loop poles. So you can see that when kc value is 0, then you are starting at open loop poles. But when kc is infinite, let's say in this particular equation, when kc is infinite, what roots you are going to get? Tell me. When kc is infinite, in that case, you will have, how many roots are there? 1, there are 2 and 1 more here, isn't it? So total number of roots are 4. So when kc is infinite, in that case you will see that 3 roots will be infinite and one root will be actually equal to open loop 0. Okay, open loop 0. What is the open loop 0 here? Minus 2.25. And that you can see here, as I increase the value of kc, this P1 which is starting from minus 1.45, it is actually approaching to a value of minus 2.25. So you can see, and these 3 roots will actually move to infinite. So you can see that these 3 roots will continue as asymptote, whereas this root will be actually start from the open loop pole and it will get terminate at open loop 0. It will get terminate at open loop 0. Is it clear? So we will see some rules. as we will go ahead, and you will see that all these rules are actually based on these concepts. Really interesting. Very, very interesting. How the concept of complex number is used and derived all the rules. Okay. Alright. So let's plot these. If we plot these, how the locus of these roots are varying when kc is varying from 0 to let's say 100. In that case, you will see that these are the open loop poles. This is P4. This is P2 and P3, isn't it? And this is P1. So you can see that as the value of kc increases, this P1 will actually move from minus 1.45 and it will approach to a value of minus 2.25, because minus 2.25 will be 0, open loop 0. And these two loci will continue as asymptote and their values will become minus infinite. Similarly, this particular loci will start at open loop pole and it will also go to a minus infinite. Okay. Looks really complicated here. But there is a logic. We will again come back to the logic that this entire root locus you can draw easily. You can draw it easily without doing a cumbersome mathematics. Remember why Raoult stability criteria we have studied? We have studied the Raoult stability criteria because we don't want it to do that difficult mathematics to find out the roots. But then we argued saying that root locus is required, because unless we know the location of the roots, we will not be able to say what type of response I am going to get. Isn't it? So both the things are there, but I wanted to get away with the complex mathematics. Isn't it? There are several rules. If you apply those rules, you do not require a complex mathematics. You can draw this entire root locus without actually finding the roots. Okay, that we will see as we go ahead. Now in this particular figure, again you can see that these 2 points are very, very important. Why? Why these 2 points are important? So these 2 points are actually corresponding to a Kc value around 50. If you go beyond this Kc value equal to 50, actually, then these roots are going to cross these imaginary axes and you will have a real part which is positive. And that means your system is going to be unstable. So this value of Kc is actually referred as ultimate controller gain Ku, beyond which your system becomes unstable. Okay, is it clear to everyone? Is it clear to everyone? Okay, let's look at some mathematics here. Okay, before we understand these things little bit in more detail. So what is the characteristic equation? 1 plus g equals to 0, isn't it? So 1 plus this g is nothing but what? gf, gc, gf, gm, and that should be equal to 0. Now this entire multiplication of all these transfer functions, that I can represent in terms of the ratio of the 2 polynomials in S, where this particular polynomial is going to give me open loop 0, whereas this denominator is going to give me open loop poles. Correct? If I equate this numerator to 0, then I will get open loop zeros directly. And if I equate the denominator equal to 0, then I will get open loop poles directly, isn't it? And this k is a constant. K is a constant. Okay. So this equation is clear to everyone. How this equation we are getting? Is there any doubt? Anyone? Please ask me if something is not clear, because we are going to again make things more and more complex. Okay, so if this part is clear, let us concentrate only on the second part. Okay. Now this z of s is what? Z of s is the equation polynomial in S which will give me the 0 if I equate to 0. Correct? So there are, let's say the order of this z of s is, let's say, m. So how many zeros I am expected to get? If the order of z of s is m, how many zeros I am expected to get? M zeros I am going to get. Similarly, this p of s is, let's say, having an order of n. So how many poles I am expected to get? N poles. Isn't it? So each of these zeros are nothing but what? Each of these zeros are nothing but the factors of this equation z of s equals to 0. Each of these zeros actually representing the factors corresponding to this equation z of s equals to 0. So I can write down this z of s in terms of these roots. So I can write down this z of s as s minus z1, s minus z2 all the way to s minus zn, where z1, z2, z3 all the way to zn are the zeros. These are the values of s at which my numerator becomes 0. Correct? Similarly, P1, P2 all the way to Pn, these are the roots of the denominator. Isn't it? So that means nothing but what? P1, P2, P3 all the way to Pn, these are the open loop poles. Isn't it? So I can write down this P of s in terms of the open loop poles as s minus P1 into s minus P2 all the way to s minus Pn. Correct? So if I write down this particular factor as k into s minus z1, s minus z2 all the way to s minus zn divided by s minus p1, s minus p2 all the way to s minus pn, there is no problem. Do you all agree? Do you all agree with me? Is it correct? Does it make sense to everyone? Why we are writing like this? Now look at what is s minus z1 actually. S minus z1 is a complex function in a way. Although it is a, you will get s equals to z1 directly, so it's a complex function. S is a variable in a complex plane. S is a variable in a complex plane. So each of these factors which are there in the numerator and denominator, all are the complex functions. And what is the property of the complex function? Any complex function can be represented in terms of its magnitude and phase angle, isn't it? So I can represent each of these factors as, like s minus z1, I can represent as magnitude s minus z1 into e raised to the power phase angle phi 1 j, isn't it? Phase angle and the magnitude we can represent without any problem. So all these terms we can represent in terms of the phase angle and magnitude. Correct? Another important thing to note down, for all practical purposes, this I have said earlier also, for all practical purposes you will find that the order of this function Zs will be lower than Q of s, lower than or equal, it will not be more than that. There is a reason. If the order of this Z of s is more than Q of s, you are actually trying to get the values which are going to occur in the future time, which is not possible in real life. So for all practical purposes, Z of s will have a lower or equal degree compared to P of s. Okay, we will prove this fact. Please remind me when we will again look at it in a little bit more detail. Please remind me. We will prove this. Okay. Now let's look at this equation again. So this is the equation we have. Now all these factors are actually the complex function. I can represent each of these factors in terms of the magnitude and their phase angle. So here this sine angle is given, isn't it? So s minus z1 can be represented as mod s minus z1, which is the magnitude, into e raised to the power j phase angle s minus z1. So you can see that all these factors are represented in terms of the magnitude and phase angle. And this entire term should be equal to minus 1. Why? Because 1 plus g OLTF equals to 0. So see this g OLTF is equal to minus 1. Correct? So this is equal to minus 1. Now when we will get the minus 1 in a complex plane, minus 1 will be, this minus 1 I can represent as magnitude 1 into e raised to the power j into 2I plus 1 pi. Isn't it? So e raised to the power, so this e raised to the power, this particular term can be represented as what? It can be represented as sine cos theta minus I sin theta. Isn't it? Something like that. Correct? So now in this particular case, you can see that if you put this 2I plus 1 pi, you will get a minus 1. You will get a minus 1. So I can represent this minus 1 as magnitude 1 into e raised to the power j into phase angle 2I plus 1 pi, where the angle is odd multiple of pi. The angle is odd multiple of pi. And this, भैया बता दो क्या दिक्कत है तुम्हें, बता दो, कुछ तो बताओ, अभी मैं समझना ही चाहता हूँ, बताओ क्या दिक्कत है. चलो I have ignored 2-3 times, but it becomes routine habit. देखो मैं whenever I am picking up somebody, I am not picking up them for the first time. I observe them first time, I ignore them second time, and I pick them in the third time. I have in the starting I have told you, if there is something important, you ask him. If something is not important, then you concentrate. Again you have done second time, then I have ignored. Now it is third time. कुछ बता दो क्या दिक्कत है? If I am wrong somewhere, or if you know more than me, please come and please explain your friend. Maybe that is okay. यहाँ तो कुछ करते नहीं हो, क्विज में कॉपी करते हो. क्विज में कॉपी करते हो. That I have seen. Okay, I remember your face. पीछे आप दिखा रहे थे. I have again told you. This is not good. जहाँ ध्यान देना है वहाँ ध्यान देते नहीं, और जो नहीं करना है वो करते हो. See, I don't like. अभी मैंने आप जैसे I have picked you up now. I don't want to pinpoint anyone. I don't like. pinpoint anyone. But then you are compelling me to do that, isn't it? अब आपको समझ में आ गया होगा, है ना? जरूरत थी इसकी, नहीं थी। Why to do that unnecessarily? मुझे भी अच्छा नहीं लगेगा, यहाँ से डालूंगा तो मुझे अच्छा नहीं लगेगा, जिस स्टूडेंट को खाली बिल्कुल बोल दिया, ठीक है? तुम्हारा तो दिन खराब हुआ ही हुआ, मेरा भी हो गया इस चक्कर में। So please pay attention. This is very very interesting. So see, otherwise you will miss. फिर उसके बाद कॉपी करोगे otherwise please. ठीक है? समझ लोगे तो फिर करने की जरूरत नहीं पड़ेगी, फिर तो तुम्हें खुद ही आ जाएगा। Okay. So here you can see that this phase angle is odd multiple of pi. Odd multiple of pi. Now it's very very interesting. Why? This entire equation we have obtained as 1 plus g OLT equals to 0. That 1 we have taken on the other side, that becomes minus 1. But let's say I would have had a negative, instead of negative feedback system, let's say I would have had a positive feedback system. So if I have a positive feedback system, what type of equation I am expected to get here? 1 minus g OLT equals to 0. So that 1 will go on the other side, so what you are going to get? You will get a positive 1. In that case, this will not be an odd multiple of pi. In that case, it will be even multiple of pi. Okay. This was one of the question I have given. फिर आप कंप्लेन करते हो कि questions are difficult, isn't it? ध्यान देते नहीं हो और फिर बोलते हो कि questions are difficult. You have to pay attention to the details. ठीक है? So then, in that case, it becomes even multiple of pi. Even multiple of pi, and all your rules changes based on that. Okay. Okay. So now here, both these equations. Once we have represented an equation like this, now you can compare your magnitude with magnitude on the right hand side, and you can compare your phase angle with the phase angle on the right hand side, isn't it? So what will be the phase angle here? Tell me. This is the phase angle S minus Z1, S minus Z2, S minus Zm, and all these will be added. Why? Because these are exponential terms. So what will happen to the exponential term? If I combine all these exponential terms, what it will be? This will be added, isn't it? Even though there is a multiplication sign here, but these are multiplication sign with respect to the exponential term. So it will be added. So you can see that the phase angle S minus Z1 plus S minus Z2 all the way to S minus Zn minus, because these are present in the denominator, minus S minus Zm, S minus P1, S minus P2 all the way to S minus Pn. So this subtraction of the phase angle of the zeros and the phase angle of the poles, that should be equal to the odd multiple of pi. Odd multiple. Okay. So you can see this phase angle you get as a odd multiple of pi. So what it means? It means that if you are finding out the phase angle manually for each of the open poles and zeros, and if their summation comes out to be minus 180 or 180, odd multiple of pi is what? 180, isn't it? In that case, each of these points are actually part of the roots. That's what it means. Remember, in this case, what we are trying to find? We are finding out the locus of the roots. So we wanted to find out where the points are located. I want to find all the points such that they satisfy this particular equation, which is called as the angle criteria. It is called as the angle criteria. Then there is another thing. See, I can compare the magnitude. So if I compare the magnitude K into this modulus S minus Z1 into S minus Z2 all the way to S minus Zn divided by S minus P1, S minus P2, S minus Pn, all these magnitude terms will be equal to 1, isn't it? So using this angle criteria, I will be able to find out whether this particular point S is a part of a root locus or not. Once I confirm that this point S is a part of a root locus, then I can find out its distance from this Z1, P1, P2, Pn, and then I can find out what is the value of K corresponding to this point. So that means I am going to find out what is the value of Kc corresponding to this point. Okay, correct. So angle criteria is going to give you a location of the roots, and magnitude criteria is going to give you what will be the corresponding value of K at that point. Okay, and both these information are required. Alright. So the same thing is kind of explained here in this particular diagram. So you can see that let's say I am arbitrarily selecting a point SC. I wanted to determine whether this particular point SC is a part of a root locus or not. How I can do this? First I have to check a angle criteria. So what is angle criteria? This particular point SC, what angle this particular point SC is making with each of these open loop poles and zeros. Remember, open loop poles and zeros I can make it directly. If this is the equation, see in this particular equation I can easily find out open loop poles and zeros. Isn't it? When the value is, so see when the value of Kc equals to 0, I can find out S equals to minus 1.45, S equals to minus 2.85, S equals to minus 4.35. So all these open loop poles I have found out easily. Similarly, I can find out open loop 0, which will be minus 2.25. But what about these points, these in between points? Finding these in between points is not easy, isn't it? Finding these in between points are not easy. So here, what we are going to do is we are going to use a angle criteria and magnitude criteria in order to make sure that arbitrarily selected point is actually a part of a root locus or not. Okay, so that's what we have done here. So we have taken any arbitrary point SC, then that arbitrary point SC, what angle this particular arbitrary point SC is making with open loop poles and zeros we have found out. So for instance, this SC, what angle this SC is making with P2. So that is the angle theta 2. SC is the arbitrarily selected point. We wanted to find out whether this point is a part of a root locus or not. I have arbitrarily taken one point in a complex plane, and I wanted to see whether this particular point is a part of a root locus or not. Looks very difficult procedure because you can have infinite number of such arbitrary points, isn't it? We will again come back. How intelligently we can do it, isn't it? Let's say this SC is an arbitrarily taken point in a complex plane. Remember, this is the complex plane, imaginary axis, real axis, isn't it? Then I am going to find out what angle this particular point is making with Z1. So that is angle is alpha 1. What angle this SC is making with P1, that is theta 1. What angle this SC is making with P2, that is let's say theta 2. Isn't it? Then whether this particular point is a part of a root locus or not, how we can find out? This alpha 1 minus theta 1 minus theta 2 should be odd multiple of pi. That is the angle criteria. Isn't it? Whatever the angle this particular point is making with the poles minus whatever the angle this point is making with the whatever the angle this particular point SC is making with 0 minus the angle made with poles should be equal to odd multiple of pi. That's what we have seen here. See? These are the angles with respect to 0 and minus these are the angles with respect to poles, and that should be equal to odd multiple. Correct? So once we have done that, let's say in this particular case, let's say we have taken alpha 1 minus theta 1 minus theta 2, and let's say that comes out to be 180. In that case, this particular point is a part of a root locus. Once we have confirmed that this particular point is a part of a root locus, then the next procedure is what is the distance of this particular point from Z1? That will be the magnitude. Similarly, what is the distance of this SC from P1? That is the magnitude. Isn't it? And what is the magnitude criteria? K into this distance divided by multiplication of all these remaining two distances. That's what we have written. And we can back calculate the value of K. Okay. So this is how we have to apply the angle criteria and magnitude criteria in order to generate the entire root locus. Now the question here is, even though this procedure I have tried to explain in a simple way, but implementing is not easy. Why? Because in a complex plane you can have infinite number of starting points. Which point you should be selecting? Isn't it? Correct. Again, another interesting fact to know here is, whenever we are drawing the root locus, remember complex roots always occur in a conjugate pair. Isn't it? So you only have to draw a root locus in one upper half and its mirror image will be in the lower half. Isn't it? Correct? So that's what is written here. So you have to only plot for the upper half and the lower half will be just a mirror image of that. Okay. Now there are several rules to plot it. Why? Because this procedure is correct, but it is going to be very difficult in implementing. Why? Which point should be selected in a complex plane? There are infinite number of points. Isn't it? Correct. So there are 6 rules given by Evans. And if you follow these rules, without doing mathematical calculation, you can actually draw a root locus easily. Without doing a cumbersome mathematics, you can draw the root locus easily. What these rules are? So first rule is the number of loci or branches is equal to the number of open loop poles. So depending on how many number of open loop poles are there, those many number of loci will start. Rule number 2 is the root loci start at the open loop poles and they get terminate at open loop 0. Okay. Open loop, the loci are going to start from the open loop poles and they are going to terminate at open loop 0. Let's say, remember we said that the number of open loop poles will be always greater than equals to number of zeros for all practical purposes. Isn't it? So clearly, very often the number of poles are more than number of zeros. Isn't it? So not all the loci will be starting from the open loop poles will terminate at 0. There will be some loci which do not have a place to get terminated. So all those loci will continue as asymptotes and they will terminate at 0 equals to infinite. Okay. So the loci which are not terminating at open loop poles, these are referred as asymptotes. These will terminate at 0 at infinite. Okay. Then let's say there is a qth order pole is there. So from qth order pole, q loci will start. Isn't it? And let's say there is a qth order 0 is there. In that case, q loci will terminate at that. Okay, so multiple poles will be counted that many times. How many roots are there? Okay, is it clear? That is the second rule. Then the third rule is the real axis is a very important thing. The real axis is a part of a root locus. If you take any point and if you count the number of poles at 0, and if that number is an odd number, then the real axis is a part of a root locus. Real axis is a part of a root locus. That's what it is. The real axis is a part of a root locus when the sum of the number of poles and 0 to the right of a point on the real axis is an odd number. It is necessary to consider only real poles and zeros in applying this rule for the complex poles and zeros. This always occurs in a conjugate pair, so their effect anyway will cancel. Correct. Further, let's say there is a qth order pole that must be counted q times. And if there is a qth order 0, it should be counted q times. Okay. Maybe I can just explain a little bit here. So see, how many loci started here? These are the open loop poles. This is the open loop pole. There are 2 open loop poles here and 1 open loop pole here. So how many loci started? 1 started here, 1 started here, and 2 started here. That is rule number 1. So number of loci starting will be the total number of open loop poles. then the open loop poles, the loci starting from the open loop poles are going to get terminated at open loop 0. There is only one 0, which is located at minus 2.25. So only this loci is going to get terminated here. And the remaining loci will continue as asymptote. So you can see this is getting terminated at minus infinity. This is also getting terminated at infinity. This is also getting terminated at infinity. What is the rule number? Rule number 3. The real axis is a part of a loop locus. So take any point here. Any point here. How many poles and zeros are there on the right hand side? None. Which is 0. 0 is a even number. So this part is not a part of a loop locus. Now take any point here. Any point. How many poles and zeros are there on the right hand side? Only one. 1 is an odd number. That is why this particular part of a real axis is a part of a loop locus. Now let's take any point here. How many poles and zeros are there on the right hand side? 1 0 is there and 1 pole is there, which is a even number. That is why this is not a part of a loop locus, real axis. Now let's look at this particular point here, any point here. How many poles and zeros are there? 1 pole here, 1 0 is here, so that is 2. And how many poles are here? There are 2 poles, that is 4. So this is again an even number. So that is why this part of the real axis is not a part of the loop locus. Let's take any point here. How many poles and zeros are there on the right hand side? 1 here, 2 here, 3 and 4. So here 1 and 2, this is 3. Here 1 0 is there, 4 and this is 5. So 5 is the odd number, and that is why this entire arm will be a part of a loop locus. So you can see this entire loop locus you can draw directly by applying the rules. Directly by applying the rules. You don't have to do any mathematical calculation. Okay. भैया कहाँ? भाई साहब कहाँ? कहाँ? वॉशरूम गए थे? कब गए थे? कहाँ है बैग आपकी दिखाओ? बैग नहीं लाते? तो कैसे आते? बिना बैग के आते? आया वहाँ से ये आए थे? एनीबडी? कोई बताओ यार ये आए थे क्लास में? तुम इशारा नहीं करो. Have you seen them here sitting? कोई नहीं बोल रहा है. नहीं रुको. किसके पास बैठे थे भाई बताओ. तुम कुछ मत करो. किसके पास बैठे थे आप? चलो. नहीं कोई नहीं बताया. किसके पास बैठे थे ये लोग दोनों? कोई नहीं बोल रहा है. अरे लेकिन सर वहां बैठे थे. कहाँ? वो तो बोल ही नहीं रहा. अरे अकेले बैठे सर. नहीं चलो ठीक है. आप इधर साइड में. आप इधर क्यों करते हो? बताओ कहाँ बैठा? नहीं कौन से ब्लॉक में? अब तुम उधर देखो. दोनों को अलग पूछेंगे ना वो किस ब्लॉक में बैठे थे. तुम साथ में बैठे थे दोनों? नहीं हम दोनों साथ में. अच्छा किसके साथ बैठा था भाई ये? आप कोई बोल सकता है किसी के साथ बैठे थे? नहीं बोल रहा है. अकेले कहाँ बैठे थे यार? कौन से आई वाले रोड में? लग नहीं रहा है. मतलब ऐसा प्रूव नहीं हो रहा है कि तुम बैठे थे.
सर मैं तो इधर ही बैठा था.
हाँ भाई बैठे थे.
उठ के चला गया. उठ के बीच में चला गया.
कहाँ से? किस साइड से उठ के चला गया? उस साइड से. लगा ही नहीं है. उठ के चला गया ना.
मेरे को भी नहीं लगा तब से.
He's also not confident.
पर साइड में बैठा था.
ओके. अभी वो बताएगा आपने अटेंडेंस लगाई थी. क्योंकि अटेंडेंस नहीं लगानी है. उठ के चले गए थे बीच में. उन्होंने पहले लगाया था. अटेंडेंस कैसे नहीं लगी? वो आया था लगा ले. अब अटेंडेंस कैसे नहीं लगी बताओ? पूरा टाइम वहाँ हो गया सब कुछ. कहाँ बीच में हो गई? वो उसने काउंट कर लिए. वो देखो ले गया वो लेता. नहीं अभी नहीं लगा था. हो गई काउंट हो गई. अब बैठ जाओ. ठीक है अब बैठ जाओ. क्या करोगे? पूरा टाइम तो बाहर से अटेंडेंस क्यों चाहिए? ओके वेयर वी आर. we have done. There is another rule. There are again 3 more rules are there. Okay. Asymptotes. Now, okay, remember I said, let's say there are n number of poles. So n number of loci will emerge from n number of poles. There are m number of gibbos. So out of these n loci, m loci will terminate at m0. So remaining n minus m loci will continue as asymptote. Isn't it? Remaining n minus m loci will continue as asymptote and they will terminate at infinite. Now, the interesting part about this particular rule is all these asymptotes radiate from center of gravity. All these asymptotes radiate from the center of. Please pay attention, otherwise you are going to make mistake. I am again saying one more. All these asymptotes are going to radiate. This word radiate is very, very important. All these asymptotes radiate from the center of gravity. How you calculate the center of gravity? You calculate the center of gravity by using this equation. Summation of Pj minus summation of Zi divided by n minus m. Okay. Another interesting thing is all these asymptotes are going to make an angle with a real axis, and that angle is given as pi into 2k plus 1 divided by n minus m. So odd multiple of pi divided by n minus m. That is the angle they are going to make with the real axis. Okay. Again, each of these asymptotes are going to make an angle with each other. They are going to make an angle with each other, which is 2 pi by n minus m. 2 pi by n minus m. Why this is important? Because all these rules will enable you to draw a rough sketch of your root locus. Once you draw a rough sketch of a root locus, then you take a point nearby that rough sketch and apply the angle criteria and see whether it is matching or not. Okay. Another important thing to note down, all these rules are, it seems like these are, somebody has given these rules just based on some empirical rules. Is it? These are not empirical rules. All of these rules you can derive. All these rules you can derive directly from this equation. All these rules can be derived from this equation. In fact, I have asked one of such questions earlier. You can derive all the rules from this equation. And considering you all being a JE pass, JE graduate, done JE exam, I am expecting all of you to prove all the rules based on this equation. Okay? You can prove all the rules based on this. At least the rule number 1, rule number 2, rule number 3 is very, very easy. You can do it directly. Remember, we said the real axis is a part of a root locus when the summation of the poles and zeros on the right hand side becomes an odd number. From where that odd number is coming? That odd number is coming because here the angle is odd multiple of pi. If it is even multiple of pi, then that rule changes. It becomes even number. So you can change those rules depending on your situation. Don't apply this blindly. Otherwise you will end up with doing something wrong. And don't then blame me that the questions are out of box. They are not out of box. They are only making you to go beyond what is done. Okay? We will stop here. We will again continue all these rules. So please pay attention. Go through this material. This is going to be slightly more difficult as we go ahead. Last class.